Okay, so we want to prove that x dot x equals magnitude of x squared. That's question 1 there. X dot x equals magnitude of x squared. So I said these proofs come in 2 forms. The first way you can prove something is by replacing the vector with something general, like, for example, let x equal x1, x2, x3. So then this becomes x1, x2, x3 dot x1, x2, x3 equals magnitude of x1, x2, x3 squared. So here we want to show that, here we have x1 by x1 plus x2 by x2 plus x3 by x3 equals magnitude squared, and the magnitude is the square root of x1 squared plus x2 squared plus x3 squared. So this is x1 squared plus x2 squared plus x3 squared. And this is the same. So we've proved this one. This is the end of the proof then. So this is what I mean by the first type of problem. It can be proven by making a replacement. Once you write that down, I'd like you to try the next one. I think the next one is a dot b equals b dot a, is it?
Yep.
Yeah, so try that one for me. You got the a dot b?
Yep.
I still see people writing. So 1 more minute and then I'll prove it. Okay, good. Now you look like you're finished. So the next example here is to prove that a dot b equals b dot a. So we again say let a equal something general like a1, a2, a3, and b equal to b1, b2, b3. So a dot b equals b dot a means you have a1, a2, a3 dot b1, b2, b3 equals b1, b2, b3 dot a1, a2, a3. So when I multiply the left I get a1, b1 plus A2B2 plus A3B3 equals B1A1 plus B2A2 plus B3A3. Which is the same thing, isn't it? A1B1 plus A2B2 plus A3B3. A1B1, A2B2, A3B3. So that proof is finished also.
Can we stop at the first line, or should I write the second line?
You could probably stop with this line here. I'm just making it extra clear. Got it? Yeah? Can I scroll down? Yeah. Okay. I will give you one more like this to do, and then I'll do it, and then I'll show you the second type. So I think most people are happy with the first type. It's not too difficult. Prove this for me. A dot B plus C equals A dot B plus B plus A dot C. So prove that one for me. Okay, it's the same deal. So A1, A2, A3 dot, and this one here will be B1 plus C1, B2 plus C2, B3 plus C3 equals A1, A2, A3 dot B1, B2, B3 plus A1, A2, A3 dot C1, C2, C3. So when I multiply this together, I'll cheat a little bit because I'll just say A1 times B1 plus C1, etc. for the 2's as well. It'll be the same, A2, B2, C2, A3, B3, C3 equals A1 plus B1 plus etc. plus A1, C1 plus etc. for the 2's as well. So this will be A1, B1 plus A1, C1 plus etc. equals A1, B1 plus A1, C1 plus etc. I got this here, and I got this here, I got this here, and I got this here. And the etc. is just me saying A2, B2, everything else. The same thing, but with 2's and 3's. And that proof is finished also. So these types of proofs are not very difficult to do. The next type can be a bit tricky. So we'll go on to the next example. Can I scroll down? Yeah. Oh. I'm waiting for a couple of people. Okay? Yep, okay. So the next type of proofs, I would call them geometry proofs usually. There's some picture or some shape and they say prove this about the shape. So for example, we have a square. O, A, B, C. And what would you call this line here and this line here? What are these called? Yeah? What are they called, do you think? Oh, that is true, they are the lines of symmetry. I was thinking of another word though, but that's true. Does anyone know what these lines are called? No, they begin with a D. D-I... Diagonals. Maybe you don't know this word. You know diagonal? You know it? So anyways, we have a square, and it's like prove that the diagonals are perpendicular. Yes. Yes. Okay, so if I was writing this as a vector, you suggested proving something is perpendicular. So you can prove this by showing. So what do we need to show? Yeah, but if we just talk about vectors, so we use the words vectors, we want to show which vector is perpendicular to which vector. AC. Yeah, well, that's perpendicular to OB. Or if you want to say it the other way, B is perpendicular to AC. And as you said, that means you want to show that B dot AC equals 0. That means you want to show that B dot C minus A equals 0. So we need to show that B dot C minus B dot A equals 0.
Why is C minus C?
Oh, you know this.
C minus C is like KC.
I knew you knew it. Now, if I go back to my diagram, let me see, is vector C? Yeah, what is vector C the same as? Oh, C, what's that the same as?
What's C?
AB. So, I think what I'll do is I'll replace that C with AB to keep everything the same letters, A and B. So again, this is B dot B minus A minus B dot A, and again I multiply it out, B dot B minus B dot A minus B dot A equals 0. I'm sorry, A. So everything is okay. The B dot AC, B dot C minus A, B dot C minus B dot A, C is the same as, oh, I think I wrote something wrong. Did I, C is the same as AB? Yes, I did, which is B minus A, B dot B minus B, okay. Now we need to clean this up a little bit more. So I'll just go back to the diagram, have a look at our A's and our B's. A and B. To be honest, I don't really like the B vector there. I would rather replace, I think I replaced it the wrong way. I replaced the C. Maybe I should have replaced the B. Now look, this is the thing, this is what makes these difficult. You don't really know which way you're going. The reason I feel like I replaced the wrong thing here, I replaced the C, I guess because the reason I replaced it is there's only one C here, so I thought it would be easy. But in fact, this looks now kind of difficult. I think it would have been easier to replace the B, even though there's two of them. I should replace the B with A plus, yeah, no, look here, what would the B be? A plus AB, yes. And what's AB the same as? C. So in fact, B could be replaced by A plus C. Let's try replacing it that way. Now you can keep that there, because we're not even sure if this other way is going to work. So I'll just take it back from this step and replace it instead. I'm replacing the B with A dot C, A plus C. Dot C minus A dot C, sorry, not dot, A plus C dot A. So this will be A dot C plus C dot C minus A dot A minus, now we're talking. This is what happens here.
You cancel out?
Yeah, but what does this A dot C cancels with C dot A?
You're left with CC and D.
Yeah, so you're left with C dot C minus A dot A. Now you might say, these don't cancel. But watch this. I can take the A dot A to the right. What does A dot A equal? A dot A is the same as what? Yeah, not quite A squared, you're leaving out a word.
Magnitude A squared.
Magnitude of A squared. And what's this here? Magnitude of c squared. Now, is the length of A the same as the length of C? If you look at the diagram, is the vector A the same length as vector C? Why? It's a square. So is this true? Yes. And now this is the end of the proof. So this is the thing. When you were looking at it here, you were thinking, I'm trying to make it equal to 0. But in fact, it turned out what you ended up showing at the end is that these two lengths are the same. So the proof is finished now. But of course, you had no idea at the start that this is where you would need to end. And that's what I mean by these can be difficult, and it's difficult to say this is how you do them. Because you can't tell from looking at it. Now I'll give you one to try. In a second, just. So we know that this path didn't help us. This was no help. You got this? Yeah? I can scroll down? Okay, this is one I want you to try and prove, and then I'll show you it in a minute. I think you should remember this from middle school. If you have a semicircle here, and here's the origin, and I draw a triangle, I draw a triangle so that there's a point here and there's a point here, and the third point on the triangle, the third vertex, is anywhere on the semicircle. So for example, if I just put it here, it can be anywhere. And then if you make a triangle, we can know something about this angle. Does anyone remember this from middle school? Yeah, this is always 90 degrees. So it actually doesn't matter where I put the third vertex. This is always going to be 90 degrees each time. So what I want you to do is to prove that using vectors. So what we'll do is we'll just give these points a name. So we'll call this one here A, we'll call this one here B, and we'll call this one here OR. And you would want to prove that this vector is perpendicular to the other vector there. So I'll give you a minute to try it. See if you can prove it. Like the last question, that it's perpendicular. You think you got it? You think it's right? Let's see. Oh no, I can see from here. Yeah, that's right. Yeah. Okay, we'll go through the proof for this one. Oh well, you want to see it now? Are you able to try it? Successful or unsuccessful? Everybody else? Okay. So we want to prove that OR A is perpendicular to OR B.
Is it the same as AR?
Yeah. So that means we want to show that OR A dot OR B is equal to 0. So that means we want to show that A minus OR dot B minus OR equals 0. So that means we want to show that A dot B minus OR dot B minus OR equals 0. So we have A dot B minus A dot OR minus OR dot B plus OR dot OR equals 0. Okay. A dot OR. Let me have a look here. A dot OR and then OR dot B. Now there's too many letters here. There's a little trick here you can do with the A and the B. Vector B is the same as what? It is, but with a minus. Pointing to the left. So if I'll swap B with minus A. So then this will be minus A dot A minus A dot OR. I'm swapping the B, so that'd be plus OR dot B plus OR dot OR equals 0. Yeah. Oh, sorry, I didn't replace this B here, did I? Sorry, I did replace it, but I still wrote it as a B. That should be an A. Now, two things cancel here. What two things?
The RA?
These two here. So you're left with minus A dot A plus OR dot OR equals 0. So you have OR dot OR equals A dot A. But what is OR dot OR?
Magnitude of R squared.
Yeah, magnitude of OR squared. And here, magnitude of A squared. Now, are these equal though? Yeah, why? They're both the radius of the circle. If you go back to the diagram here, this magnitude here of this vector is the radius, and this one here, its magnitude is the same. They're both equal to the radius of the circle. So this is the radius, and this is also the radius. So that ends that proof.
Do we have to look at the OED?
The QED? No. What's wrong with you, Yusra? Sorry, there's many things wrong. What's wrong with you now? Nothing? Alright. I suppose in both proofs I did, we ended up showing that one length was equal to another length. But I think that's only because of the two examples I picked. Sometimes everything does cancel and you get it equal to 0 if you were showing something was perpendicular. Just in the examples I did, it wasn't the case. Which one have I seen in the exam? I believe I've seen something like both of these in the exam. Section B, yes. But the last worksheet is more common for section B than this, like I said. Okay. And section A, yes, actually, right, not section B, but there was a third question I remember seeing in the exam. I think it's the one, number 3. I believe it was something like number 3 I saw in the exam before. So you can get both types for the exam. And in fact, I think it was the question I did with the square and number 3 were both in the same section B question. I think they came up the same year. There was 2 proof parts of that question. Okay. I'll let you try these for a few minutes. Yeah, try to prove some of these for a few minutes then. And then later today we have the last section of the chapter.